Okay, here's some additional examples. This is from another textbook, Sengel. It's a competitor. And I think that's the author of the thermo book, excuse me, the fluids book that we use in fluid mechanics here at UHart. So here's example 1.6. I'll do two examples, try to do them quickly. So we have a manometer. So this is a fairly simple problem where we have some kind of pressure in here that we want to try to find. We have a fluid inside the manometer that has a specific gravity of 0.85. And let's see, do we know, is there something in this tank? No, well, the pressure would vary in this tank. So if we had to find the pressure, we would need to know a location if this was a liquid. But we will just go ahead and try to find what the pressure is at this location. Maybe this is a gas inside here. So this distance right here is 55 centimeters. And the local atmospheric pressure is 96 kilopascals. So we want to determine the absolute pressure within the tank. So let's switch over to the document camera here and work through this problem, which I didn't queue up over here. Okay, there you go. So this is a pretty straightforward one. So let's try to start getting into a better habit of doing our givens. And as I've said before, maybe you didn't hear me, so I'll repeat it. This is a good practice to try to do when you're doing work, to try to start writing down what you know and then what you want to find. It's where your brain starts moving. So it gets you started into things and will be beneficial. And it's a good habit, and then when you go to an exam, you have that habit, you can go back, you can rely on that, and you get your brain kind of working similar to how you've practiced. So here, I'll write the specific gravity is 0.85, and of course that's a way to get the density, or the specific weight. You just have to multiply that by the specific weight or the density of water. And let's see the height, let's call h. I like little h better than big H. It's 55 centimeters, which is 0.55 meters. Divide that by 100. That's the easiest way to remember that. And let's see, the atmospheric, we'll call it PO, it's going to be 96 kilopascals. And find, we just called it P, so we'll call it P. All right, so we had started to think about the things that we had to do. In manometers, we want to do like a swim down approach, right? So here is actually where we're going to find the P right in there. We'll assume this is a gas. If it was a gas, then it would be the same pressure here, up here, and everywhere, basically. But if it's a fluid, it varies, right? The pressure's low here and gets higher as it goes down. So I like to say we start with, this is the thing we want to find, and this is our destination. And so here's our starting point. And we're going to swim downwards 55 centimeters. So downwards is positive, and you could go, this is what I'm used to, what most people do right here. And we don't know what this thing is, so I'll call it liquid. And times H, which is also, we could also write that density of the liquid times gravity, and then times H. So let's rewrite this thing out. Let's go to basic units. So I'm going to go 96,000. We know those are newtons per meter squared. That's what the 96 kPa is going to be. And then plus, and then, so the liquid, okay, so people might argue about the density of water, and for whatever reason, people like to be very, very picky about it and say that it's 999 kilograms per meter cubed, excuse me. I personally think just go ahead and use 1,000. What the hell? But anyway, so when we want this density of this liquid, that we'll write it up here. The density of the liquid is going to be the specific gravity times the density of water. It'd be like standard water, standard temperature, which I think should be 1,000. These people said 999, so I'm going to go with the 999. I guess maybe I'll concede. Sure, why not? It's not like it matters that much to me. But anyway, I started units over here, so we'll continue with the units. Kilograms per cubic meter. And what did I say? Oh yeah, we need 9.81 meters per second squared. And then the height of 0.55. Did I do everything correct? And if you run all those things out, we get a P of 100,582. These are Newton per meter squared, which is the same thing as a Pascal. And so we might as well divide it by 1,000 because that's usually the thing to do. And we only need 4 sig figs. So let's go to 100.6 kilopascals. And do me a solid at the end of every problem. Wait to the end, rewrite the thing out. We could go 101 if we wanted to. But there's actually a silly little extra rule in the answer sig figs. Comes out of Beer Johnston's book, I like a lot, that if the first digit is 1, then answer with 4 sig figs. If the first digit is anything other than 1, answer with 3 sig figs. And I think that's a pretty good policy to go by. So that was a pretty easy problem. Let's go with a more complicated problem. This is actually sort of like a real thing that you would actually do. This is like someone's invention just to make students' lives difficult. And of course, I have to do the same thing. Because you have to think a little bit more and use the technique that I described. It's not too much more difficult. It's just a little more challenging. All right, so let's read the problem. That's a good place to start. Water in this tank right here. It's got pressurized air in here, so I like that you'll draw a little pressure gauge on there, a little tiny pressure gauge, and it's pressurized by air. And this actually happens. Okay, by the way, that we actually would pressurize a tank like this with air. I think you probably have one in your home, in a lot of people's homes. It's there's like a bladder inside here where I don't think the air touches the water, but I think that it does keep your you could pressurize the thing, keep it at constant pressure. The tank is located on a mountain. Okay, that's good to know. With an altitude of 1,400 meters, where the atmospheric pressure is 85.6 kilopascals. You could have looked this up. I think you could have looked that up. It might be in the appendix. There might be a table for it. For like a typical thing, but you actually might even be able to calculate this now that I'm thinking about it. Yeah, you might be able to calculate this. Let me think about that a little bit later. Okay. Determine the air pressure in the tank if we have a height right here of, all right, so let's write this down right here. So PO is 85.6 kilopascals. You're going to have H1, keep track of this, 0.1 meters. And H2 is equal to 0.2 meters. And H3 is 0.3? No, they just messed with us. 0.35 meters, you bastards. Take the densities of water, oil, and mercury to be, all right, so water, we go H2O. Sometimes I go WTR. I don't know. I'll mix it up. Keeping life exciting. 1,000, see this, I told you, 1,000 kilograms per cubic meter. Told you. That's what most people use that, I think. Density of, what do we got? Oil is going to be 850, right? So its specific gravity is 0.85. You notice that, right? 0.85. Easier to do. Easier to think of. Yeah. And then mercury, go HG. HG wells, 13,600 kilograms per cubic meter, which is pretty typical. And we want to find the pressure of the air. All right, so here's our destination. Here's the place we're going to start. Let's go PO right here. So we're going to say that P air is going to be equal to, and we're going to swim down. Okay, it's hard to tell the colors right there because of the things right there, but right there. Okay, so we're going to swim down until we get to this interface. So that's going to be the H3. So we're going to swim down, and that means we're going to go plus. So we're going to go, and this is H3 is the mercury. Which did they tell us which one? Yes, right there. There's mercury. So we're going to swim down. So we're going to go density of mercury times G, whoops, you're not in there. Density, number G, H3, right? We're gonna jump, we're gonna go down to here, and then we're gonna swim, boom, swim over. And now we're gonna go up to here of oil. Like this right here, this little part right here, that's trying to fool you, right? It didn't need to be this high. That thing could have been, This thing could have been much lower right there. They're tricky, but we're going upwards in the oil. We have to swim upwards to the oil. So we'll go here and go oil, gravity, and that is going to be a distance h2. It's kind of weird how they marked that out. They marked it out. I didn't draw this one. Okay. Anyway, so that's going to be h2. And then we're going to have to swim up to right here, and that's, of course, the surface right here. So this pressure right here is going to be the same pressure as right there. Is that true? Wait a minute. No, I'm sorry. Wait one second. We're going to have to, I think I did this wrong. Did I do this wrong? 1 second. Let me think. You know what happens? Okay, so this is actually the right way to do it, what I was about to do, but this is what you would have to do, kind of. Let me see here. We'd have to swim up here, and then swim up to here, swim over, swim down, yeah. So I'm going to swim up to right here. That's correct, right? And then we're going to, pause, 1 second. I just confused myself. Shit. Got it. Talking myself out of it. All right. Swim down, positive. Swim up. Yeah. Yes, that's right. Okay. Swim up through the oil to right here. This is the same pressure as here, which is the same pressure as right there. See, that's what happened, is we came right in here. That has to be the same pressure, right? Because this right here is the same pressure here. So like in oil, this is the same pressure as right here. And so this pressure in the oil is the same pressure as the water. And so same pressure in the water from here is the same pressure the water is there. Okay, great. So what we have to do is swim up an additional. So here you go, is the H2O, gravity, and then H1. So let me go through that again, all right? Start here at this pressure, swim down to get to here, and of course this is the same pressure as that, so we swim over, nothing changes. We go upwards to right here in the oil, that H2, and then we notice that pressure has to be the same pressure as that, which has to be in oil, which has to be the same pressure in the water, right? This interface between the oil and the water, they share the same pressure. So for the water, that has to be the same one over here. So then we have to swim up to the air right here, and now we're at our destination. I know I kind of like messed it up a little bit, but anyway, let's turn this into 85,600. I'm going to leave off the units because we're going to use base units so we can be confident with the thing. So we start out with the mercury, 13,600 times our 9.81 times our H3. Where's H3? H3 is 0.35. Now we go to minus, we go to oil, 850, 9.81, and H2 is 0.2. And then lastly, minus 1,000, this is water, 9.81. And what is H1? H1 is just 0.1. I didn't bother doing the in-between numbers. It would have been interesting to see which each of these were and then to compare it to that. It's often a good thing to do. But I didn't, so we'll do it maybe in class. I don't know, probably takes longer. So we get 129,647, and these are Newton per meter squared, which is a Pascal, and then we can turn it to 129.6 kilopascals. So the answer, which we write down, looks like it says pair, doesn't it? 129.6 or 130, either or, is the answer. So there you go. Another example. This is a more complicated one. I I think it's pretty close to one of your homework problems. So that was pretty nice of me, I think. We'll see you in class.